So yeah, I'm Rhianna Mcaneny. Nice to meet you all. I'm a PhD student with IPPS8 and INRAE, so it's a French lab. And I'm working on the use of satellites for phenotyping. I'm very happy to show you my results of my first year of PhD. So if you have any commentaries at the end, I'll be very happy to hear from them. So just to give you a little bit of context, I'm doing my PhD with the FAST project. So the FAST project that is led by Raoul, that you probably heard during the week, tries to get functional traits out of structural traits thanks to functional plant models. And to do so, we need observations. And this is where my PhD stands. The observations that we gain are taken from different devices, such as drones, the Phenomobile, and satellites. But satellites are quite new for phenotyping. So the questions that we have here is how can we use those new devices and, just adapt them for our use in phenotyping. We use satellites because they're quite useful in terms of how frequent we can have pictures out of them, the good resolutions that they have today, and the fact that it's quite easy to gain information a bit everywhere on the world in different environments, and also at a low price. So just for the outline of my presentation, of course, I'll present you the materials and methods that I have that are taken from the FAST project. And then I will try and address two research questions that I have. The first one about harmonization of satellite data. As we have different kinds of satellites, we would like to know how we can gain all the information of all of them and create a kind of virtual constellation to get best of both worlds. And then I will try and assess the second questions of my research, which is improving the algorithm for estimating GAI. In fact, we're using the VerVeNet algorithm, and this is a very general algorithm that we use. So how can we specialize it? Is it interesting to specialize it for wheat, for example? So first, my materials and methods are taken from the FAST project. The FAST project is led in France. We have different kinds of sites around different environments there, and we're studying, as I said, wheat. In the fields, we have sampling that gives us the ground truth, and we also use the Phenomobile that gives us the green area index into different what we call phenotyping plots in the INRAEs in France. And of course, we're using satellites to monitor them. The satellites that we are using are the PLANETSCOPE satellites, so the CubeSats. Why are we using them? It's because we have images daily, except when there's clouds, obviously. And there's a very good resolution out of them because it's 3 meters per pixel. The only problems they have is that they don't have a lot of bands there. They have 8 bands, while the Sentinel-2 satellites has a 10-band information. But the problem is that the frequency is only from 5 days, and the resolution is 10 meters per pixel. So we use those two and combine those two informations to gain either NDVI, which is a VI, very easy to get because it's just a calculation of bands, and the GAI. So for those who are not familiar with GAI, it's basically like LAI, but it's not just for leaves. It's for everything that's green on the plants. Obviously, as you can see on the pictures here, we can't really distinguish what is a leaf and what is just something else on the plant. So that's why we use the term GAI. The GAI is obtained by the inversion of PROSAIL thanks to the VerVeNet model. So the VerVeNet model was built by my PhD directors in INRAE and uses the PROSAIL inversion. So that means that we use PROSAIL, we gain every information that we have in this model, and then we invert it to get the GAI. So to do so, we take the structure of the plants, the optical leaf properties, the soil properties, the satellite properties. And this helps us to create a virtual data set with reflectance and GAI. And then we train a neural network, and out of, obviously, we can then use real data to gain the GAI at the end. So this leads us to my first research question, which is the harmonization of satellite data. As you can see here, we have the field measurements compared to GAI obtained with the algorithm for PLANETSCOPE and Sentinel-2. I put 4 and 10 on the graphs because Planet has 4 bands that we use for the algorithm, and we use 10 bands for Sentinel-2. As you can see on the graphs, we have a little problem here that when we have high GAI, the models don't really help us get the real GAI that we measured in the field. This is something that we were expecting, since in the field measurements we have what we call true GAI. So it's like precise and accurate GAI. Well, what we have with devices such as satellites is what we call effective GAI. Of course, we can't be as much accurate as what we have in the field measurements, but it is quite a problem that we would need to address. And what we can see here is that the Sentinel-2 GAI performs better than the Planet one. And so we were thinking, okay, we have a better time resolution for Planet, we have a better spatial resolution for Planet, but we have a spectral information from Sentinel-2 that's better. How can we combine those two arguments there and find something that can help us gain a GAI that is more accurate? We can do that by harmonization. The harmonization can go from either the bands or the products. So what we have today is this. We have either Planet and Sentinel-2, goes into BeVinet, gives us a GAI. What we can use is also another model which only uses 4 bands for Sentinel-2 so that we can compare it to the Planet model. The first way of harmonization is there. We can either harmonize by bands, meaning that we take the 4 bands from Sentinel-2 and Planet, do linear regressions, correct the results for Planet into the reflectance bands, and then put them into BeVinet back again and obtain what we call a harmonized per band GAI. Or we can use the product. So that means we just basically take the GAI from Sentinel-2 and Planet, correct the Planet GAI, and see if this gives us something better. The results are here. So we can see on the first graph the comparison between Planet and Sentinel-2 GAI. You can see that there's a difference there. And when we use the harmonization per band, we see there's almost no improvement there. But when we use it per the products, so meaning at the end, we have a major improvement and the harmonization works better. You can see that on the graphs here. So the upper ones are the graphs that shows in blue the GAI for PLANETSCOPE at the normal model, and then the one that was harmonized. You can see there's no difference. The green dots are Sentinel-2. We have nothing like Sentinel-2. It didn't work. But if we do it at the product level, you can see that the green dots and the red lines align almost perfectly, which means that we managed to correct. Okay, we found a way to gain a more accurate GAI, but as researchers, we wanted to understand why this appeared and why can't we correct it on the reflectance level, which is something that we would normally do. When I was doing my bibliographical research, I came across Daniel's and our paper that showed that actually LAI and GAI are very sensitive with the SWIR bands. And so the SWIR bands are on Sentinel-2 satellites. It's the B11 and B12 bands, and you can see on the graph here that if we put the GAI with those bands, there is a kind of correlation. It's not that obvious on B11, to be fair, but it's quite obvious on the B12. So we were thinking, okay, maybe this is where the spectral information we need is. And so what we did is we tried the model with the 4 bands for Sentinel-2 and the 10 bands. That's the graph where you can see on the upper right here. So the green line is the one with the 10 bands and the blue line is the one with the 4 bands. And you can see that with 10 bands, so with the SWIR bands, it performs better. So this is probably where our problem comes from. The fact that if we use at the product level a harmonization, we put the spectral information of Sentinel-2 into Planet that was missing. What we did afterwards was to compare some models with and without SWIR bands. And what we saw is that for the model with no sphere band in green, it performs the same way than the one with the harmonization from the bands. And when we are adding just one of the sphere bands, either the B11 or B12, it performs the same way as if we put the 10 bands on the GAI model for Sentinel-2. So this is what we concluded. The sphere bands are important to do the harmonization. We need to do it at the product level so we can add the spectral information from Sentinel-2 that was missing into Planet to gain a GAI that is more accurate. The little thing I would like to show you on this graph is also that we have an underestimation at the low values. So this is the effect of PROSAIL. This leads me to my second research question, how to improve the algorithm for estimating the GAI. So as I said earlier on, we are using the BeVenet algorithm. The BeVenet algorithm is very generic. It's meant to work everywhere on Earth, every kind of culture. So it's great, but at the same time, the GAI is not accurate, obviously. So there's different ways of putting into it a priori information to help it just find and estimate the GAI more accurately. You can change it through the structure of your canopy. You can change it with the optical leaf properties, meaning you can have it crop specific, or you can use the sowed properties. In a way, we already specialized it into the satellite properties because we have one model for Sentinel-2 and one model for Planet. So this is the first question that we asked ourselves here is, how many a priori information I can add to my model to gain more accurate and precise GAI, and what is the trade-off with having a very specific algorithm compared to a generic one that would work everywhere. The other question we asked ourselves at this point was the lack of spectral information be compensated by a priori information? Meaning we just saw that the sphere bands were super important to gain a GAI. But actually, is it important if we have a priori information? So do we have a specific model that really is used for a certain type of crop? In that case, do we still need those sphere bands, or is the bands from Planet sufficient enough? So what I did, I will give you an example of just one specification, which is the sowed specification. I do have to work on the other ones, so the structure and the crop-specific models during my second year. So here you can see that actually on the NDVI or GAI temporal series, when we have what we would call PROSAIL, so that's between the green squares, we have some values that are quite high, which is not normal. We should have something like very near zero. So we would want our algorithm to take into account the soil that we're studying. To do that, we have several ways of doing it, either building a algorithm that works for each site. So every time you're trying to monitor a site somewhere, you will have to create an algorithm, a BeVenet algorithm, or you can do something more country specific. So for me, it's in France, but you could have a model for Australia, or you could have a model for Italy or whatever. Or you could use the states that you have in your project. And this is what I did at first. So what we did there is we just took the pixels of PROSAIL, because we knew when there was PROSAIL in our fields, and add them to the model. So it became what we call fast specific. The results here show that for the GAI, it helps us gain a GAI that is closer to zero, so which is meant to be the truth. But it works better for Planet than Sentinel-2, showing again that Sentinel-2 is better calibrated than the Planet reflectance bands. This is why Sentinel-2 is also our way of it's our reference. Sorry. Now the question we ask ourselves is, can it work for something less specific, like France specific? Because if every time you would want to use a model, you would need to train it for a specific site or specific experience, that would be very long. So we would try to find here a trade-off of something that is specific, but not too specific to be painful for those who wants to use it. Okay, so in conclusion, what I would want you to see here from my research are we have the GAI that can be estimated from satellite images, which is a great news. But there's a difference between true GAI and effective GAI that you need to bear in mind. And this is where we're going to use phenotyping data. Phenotyping data are the ones that we have in the INRA that are followed by the PhenoMobile. The PhenoMobile will give us true GAI and effective GAI. So then we could build a model to try and find a way to link those two together and have something more accurate in the fields. The other message is that the harmonization should be done at a product level because it will help Sentinel-2 to give its spectral information to PLANETSCOPE that is missing those SWIR bands that are quite interesting. And then we need to provide a priori information to have something more accurate. The next step for us would be to have a model that is what we would call crop specific for wheat and see if we could add some information to it, either by just the distribution and how the wheat is in the field with its leaf properties, or by co-distributions of the inputs of the PROSAIL model. And then obviously I'll study the relationship between true GAI and effective GAI. And then the last thing I need to study, and I didn't really show it here in this presentation, well, I still had time. I think I was a bit nervous about the fact that I was going to speak too much. But so I can talk about that a little. It is the fact that we have a lot of problems with geometrical corrections and PSF. So for those who are not familiar with it, PSF is the point spread function. That means that one pixel that you're studying could be contaminated, if I can say so, with the pixels around it. So the pictures, the graphs I showed you were taken in fields. So the pixel next to it is just wheat. So it's wheat impacting wheat, it's fine. We don't see a massive difference. But when we are looking at the GAI from the phenotyping areas that are 2 meters by 10 meters, there is a little problem there. We can see, for example, that so what we call PAI, but is basically GAI gained with the PhenoMobile, is very, very different from the GAI that we have from the satellites. And the satellites gave us GAI that don't go above 3 or 4 GAI, while we saw earlier on that we can go into until 12. This is due to the fact that the PSF is very big when you have roads between your microplots. And also you have a big shift. So I'm sorry, I didn't put it there, but when you look at the pictures taken from satellites, you see that between dates, your field is moving a little bit, meaning that actually from one day to another, you're probably not seeing the same pixel. Again, for a big field, this is not a big problem because you'll do the mean NDVI, the mean GAI, it's just wheat everywhere, so it's okay. But when you have a road next to it, that is a real problem, and that's why we have a GAI that is so low. So this is something I will have to study during my second year, since for phenotyping areas, this could be a major problem. So yeah, and I would like to thank all of my FAST, my PhD directors for helping me during my first year and bringing me to my first conference. So be kind. Thank you.
Thank you very much for the nice talk. Are there any questions? So we have time for a few questions.
Hey, very nice approach. I was wondering in the first part, when you do the correlation between the GAI coming from the ground measurements, planet, Sentinel. So you measure with the spectrometer on the ground to do those calibrations. We have reflectance spectrum from the ground level. So have you tried the correlations between the reflectance bands or any other vegetation indices? Because I think that they are what might be screwing up also the correlation could be the inversion of the model, because in my experience, all these simulation models work very well in the direct way, but when you invert them, then small changes can lead to very different things. So I wonder if the differences there are due to the different retrieval methods or the models applied upon them.
That's a good question. We try to gain different models to see if they all gave us the same results, so to see the impact of what the model could be. Of course, the model is also the reason why we can go up on the GAI. So that's why we push it artificially. We put unrealistic GAIs in our models to try and push it a little bit. But I'll keep in mind to use maybe other ways of gaining the GAI into the models to see if we can correct that, if that was your...
Yeah, I just would try normal reflectance indices for the correlations, because I think that maybe the train set you give to the PROSAIL model might be overestimating some situations that lead to this sigmoidal thing.
Mm-hmm. Yeah, well, I'll keep that in mind. Thank you.
Yeah, thank you for the nice presentation. As you mentioned, the main problem here is the pixel contamination, mainly with soil. I'm curious about the measurement that you did, which you mentioned you have been working on wheat, but which crop stages? Because in wheat, when you go towards the maturity, you will have a lot of problem with mixing the soil pixels with crop pixels. And that could be one reason that you have lower correlations. So I'm wondering which crop stage you have been focusing on.
We focused on every stage of wheat through the year, especially to kind of guess what the soil effect is on those different stages. So we have information at any kind of stage, and we can see that there is a contamination of soil at all the stages that we're looking at. And that's why we're trying to put the soil into the models like very precisely, because this could be a way to avoid this contamination there.
Yeah, even when the canopies develop well in the after heading stage, you don't see any difference between heading and emergence and maturity for the values, or there is a slightly difference between these stages.
Sorry, I didn't quite get that. My English is getting tired.
Yeah, it's okay. Because when the canopies develop well, then you barely could see the soil pixels, right? But at the beginning, in the emergence, you see a lot of soil pixels, and also at the end of the season, because the leaves, they drop and it's senescence and maturity. So I assume that there should be a difference between the GAI measurements in the heading stage compared to the maturity stage. So I'm just curious if you have been looking at each growth window separately, or you just pull all the data together.
I put all the data together, but actually it's a very interesting point. Maybe we could model the model in a way that it doesn't take the soil into account that much when we have the maturity, when we don't see it anymore. That's actually a good point, because when I add the soil in my models, I saw that the GAI was lower at the maturity than with the model without the soil. So maybe that's what happened there, and maybe at one point we should change the model and say, okay, counting from now, we don't use the soil anymore. That's a very good point.
Yeah.
Thank you.
One last question over there.
Thanks for the talk, very interesting. Two small questions. What is the lifetime of these CubeSats, from just to see how these models will age over time? And secondly, can you not exactly use those roads around such a crop to correct the variation from, well, one CubeSat to the next version?
Sure. So I don't have in mind how long the CubeSat lasts, but I think it's quite big. Like it's probably for, I don't know, I would say something like 8 years or something like that. And they continue adding new satellites all the time. So it compensates the fact that some could die or have any issues, and they just don't take them into account anymore, and they just add more and more satellites with more and more features. Sorry, I forgot your second question.
I was asking, can you not deliberately use that road, for instance, next to that field, because you assume that that road will stay identical over a number of years to correct your model from that point of view?
Yes, this is what we're doing with co-registration. Oh, that's hard to say. What we're doing here is you can either, there's two ways of doing that. You can either take, for example, buildings and roads that you know won't change over time and use them as points that you know should be at the same spot all the time, or you can use the reflectance directly and minimize the distance between two dates' reflectance. So far, what I'm doing is I'm trying to use those roads and buildings or any kind of information I have in the field to correct the images and put them back together in the right way.
Okay, so thank you very much.
Thank you.
For the talk.